An arrow is shot from level ground with an initial speed of 80 meters per second, inclined at an angle of 22.5 degrees. Find the position of the arrow 1.50 seconds after being loosed. Assume the point the arrow was loosed is the origin for reporting position and neglect air resistance. So that means we're allowed to use projectile motion equations, and in particular, since this is over level ground and being launched from ground level, we can use the versions we have here, where the initial positions, both horizontally and vertically, are equal to 0. And in that sense, like what it's saying there is we can assume that for this picture I've already drawn here, that the origin is right here. Since we're given an initial speed of 80 meters per second, the way I should think about that is there'd be an initial velocity vector here, maybe, I don't know, pointing something like that. That's going to have a magnitude of 80 meters per second. I can barely fit that in there. And it's at an angle relative to the ground, which is not necessarily accurately pictured here, but that angle corresponds to the 22.5 degrees. So that's kind of my picture of what's being given to me here. And then at some later time, so I'm not sure exactly at which point that is, but let's say there's some point right here, and maybe that corresponds to, again, this may not be at all accurate, I'm just kind of drawing it for sketching purposes, but let's imagine that there's some later point that corresponds to 1.5 seconds later, and I'm wondering what are the x and y position values at that point, because since it says find the position of the arrow 1.50 seconds after being loosed, that's, I think, what that is asking for. In other words, tell me what is x at 1.5 seconds equal to, and what is y at 1.5 seconds equal to. So these, again, are the formulas that we had for this type of projectile motion, but what we have to calculate here or recognize, let me look at the x one first. So if I say, okay, I'm going to do x of 1.5 seconds, the thing we need to remember is that this v naught x is really equal to v naught, and let's see, this is x, that one is cosine, right? That's always the hardest part to remember, is cosine of I'm just going to put a generic theta here, all of that multiplied, I put parentheses here because it's a little weird to put a t outside. Otherwise, someone might think it's like, well, is it the t inside or outside the cosine, is a confusion that comes up. But this v naught really corresponds directly to the 80 meters per second that I'm given. So in this statement here, where I'm calculating the x position at 1.5 seconds, I'm going to use this expression kind of as a guide for what I'm doing here and just put in 80, and I'll go ahead and keep all the units for this one, 80 meters per second multiplied by the cosine of 22.5 degrees. And then the t I'm going to replace with 1.5 seconds. And again, because of the way this expression looks, there's some ambiguity. Might be nice if I throw some parentheses on like that, so I know that when I go and put this in my calculator, don't put the 1.5 inside of the cosine. Make sure you close the cosine with a parenthesis in your calculator and then multiply by 1.5, or you can also multiply by 1.5 out front if you like, to make sure that it goes into your calculator correctly. So I've gone ahead and done that calculation, and I get like 110.865, etc. But I think given 3 sig figs looks like where we're at here, I'm just going to round that off to 111. And what should the units be? I've got meters per second times seconds, so I think this will be in meters. Makes sense. We're looking at a position, right? And we can do y in a very similar way. Y of 1.5 seconds is equal to what, in other words? Well, this one maybe is a little bit more complicated. If I go back into my kind of generic formula over here, we can recognize that for the y component of velocity, it would really be v naught sine of whatever that initial angle is in general times a t, and then there'd still be the minus 1/2 g t squared. So this is like kind of like my recipe here for what I'm going to do down here. So this is going to look like 80 meters per second times cosine. I'm sorry, this should be sine. As you can tell, I'm a human being. I think in a number of videos I've sometimes screwed up a sine and a cosine, and I've not redone them because I want to show everybody that is common. I do it too. But anyway, so if you do that, join the club. As long as you can catch it. I mean, in this case, I had it written right here, and my brain wasn't working. And then I'm going to have, let's see, maybe I'll write on this next line here, I'm going to have minus 1/2 times 9.81 meters per second squared. And I'm being very explicit with the units here, which means you need some space. I mean, I think I've got enough space here to do it. But just recognize if you write all the units, that's why sometimes I don't like to do that. Sometimes I will not write all this. I'll just look at a formula like this and then put the numbers in my calculator so I don't have to write too many units. That's why I don't like to do too many manipulations with units. But here, I'm just straight calculating. I'm done with my manipulation. So it's just a matter of putting that expression into my calculator. Of course, in your calculator, you can't put units in there, but I did put these parentheses to make sure that we recognize it's times 1.5 outside the sine of theta. But then we also have the minus 1/2, where I put in 0.5 in my calculator, times 9.81 times, don't forget to square the 1.5 there. And it looks like the answer I'm getting for that is like 34.9. I think that's rounded correctly there, 34.9 meters. So those are my final answers there. 111 meters for the X position and 34.9 meters for the Y position. Who knows if that's what I drew correctly up here, because I don't know what the rest of it really looks like here. But there it is. It looks like those were correct.